Okay, so the next transformation that we'll consider is a rotation. And here we'll use polar coordinates to make it clear what's happening with a given point. So given a point, x, y, in polar coordinates, the x component is r times the cosine of some beginning angle, which we'll call alpha, and the y component is r sine alpha. And if we rotate this point, through some angle theta, then the new point, x prime, y prime, is given in polar coordinates as r times the cosine of the angle sum, alpha plus theta, times r times sine of the angle sum, alpha plus theta. So again, x prime is r times the cosine of alpha plus theta, which using a trigonometric identity gives us r times the cosine of alpha times the cosine of theta minus r times the sine of alpha times the sine of theta. But r cosine alpha is the coordinate x, and r sine alpha is the coordinate y. So this is this is x times the cosine of theta minus y times the sine of theta. So now for the coordinate y prime, this is r times the sine of alpha plus theta, which using a different trigonometric identity gives us r times the sine of alpha times the cosine of theta plus r times the cosine of alpha times the sine of theta, which is y times cosine theta plus x times sine theta. And for clarity, I will rewrite this as x times sine theta plus y times cosine theta. And so the point x prime, y prime as a vector is given as the vector with the x prime component equal to x times cosine theta minus y sine theta. And the y prime component is x times sine theta plus y times cosine theta. This vector can be written as a product of a matrix and the vector of the point xy. And that vector, or rather that matrix, has components cosine theta, negative sine theta, sine theta, cosine theta. So notice that this does give us the correct expansion. For the x prime component, we have x times cosine theta minus y times sine theta. And for the y prime component, we have x times sine theta plus y times cosine theta. Now this matrix is known as the standard rotation matrix in the Euclidean plane. So now let's talk about a type of symmetry, rotational symmetry. A figure has C sub n symmetry if rotation about its center by 2 pi over n radians results in a shape that is indistinguishable from its original position or orientation. Now C1 symmetry means no rotational symmetry. Since rotation by 2 pi over 1 or 2 pi radians is the same as rotation by 0 radians, which is no rotation at all. A figure with C1 symmetry has no center. And we use the notation C infinity to denote perfect rotational symmetry. So let's consider the symmetries, the rotational symmetries of our conic sections. So first, we consider a circle. No matter what angle we rotate the circle about its center, we have a symmetry, and so a circle has C infinity symmetry. So now for an ellipse, in order to have a symmetry for an ellipse, we must rotate through pi radians. And so an ellipse has C2 symmetry. So now we'll look at a hyperbola. For a hyperbola, we must rotate through pi radians to have a symmetry. And so a hyperbola has C2 symmetry. Now for a parabola, we do not have a symmetry unless we rotate through an entire 2 pi radians. So a parabola has no rotational symmetry and therefore no center of rotation. So summarize, circle has C infinity symmetry. An ellipse has C2 symmetry. A hyperbola has C2 symmetry. And a parabola has C1 or no symmetry. So next, we'll talk about a third type of transformation, a reflection. So let's use an ellipse. We have reflection with respect or in a given line, respect to or in a given line. So if we look at reflection in the y-axis, then the y components are fixed, but the x components are mapped onto their negative values. If we look about at reflection in the x-axis, then the x values are fixed, or the x component is fixed, but the y values are mapped to their negative value. If we look at reflection with respect to the line y equals x, then the x and y components are switched. And so if we look at reflection through the line y equals negative x, then not only are the x and y components switched, they're also mapped onto their negative values. So to summarize, for reflection in the y-axis, and this is the line x equals 0. The point xy is mapped to the point negative x, y. So we can use vector notation. The new point x prime, y prime is the product of a matrix times the vector xy. And we can modify the identity matrix to reflect what's happening in this case. So in this example, the x component is mapped to its negative. And so we have the matrix with components negative 1, 0, 0, 1. Notice that this does give us negative x and positive y. So now if we look at reflection in the x-axis, then this is the line y equals 0. And the point xy is mapped to the point x negative y. Oops, x negative y. And so the equation for this in vector form is x prime y prime is a vector, or correction, a matrix times the vector xy. In this case, the y component is mapped to its negative, and so we have the vector 1, 0, 0, negative 1. And this gives us x plus 0, 0 plus 0x plus negative y, or negative y. So if we look at reflection in the line y equals x, the point xy is mapped to the point yx. And so the equation x prime y prime, the vector x prime y prime, the matrix that we use is the modification of the identity matrix by interchanging the x and y. So we have 0, 1, 1, 0. And this gives us 0x plus 1y, or y for the first component, x plus 0y, or x for the second component. And if we look at reflection in the line y equals negative x, then the point xy is mapped to the point negative y, negative x. And so the equation x prime y prime, the vector x prime y prime, is the product of a matrix with the vector xy. And again, not in with reflection in the line y minus x, or y equals negative x rather. Not only are the components switched, but they're mapped onto their negative values. And so we have 0, negative 1, negative 1, 0. And this gives us 0x minus y and negative x plus 0y, which is the transformation that we want. So now we can talk about mirror or reflection symmetries. So a figure has sigma L symmetry, sigma sub L symmetry, if reflection in the line L results in a shape that is indistinguishable from its original position or orientation. So again, we'll start with the circle. Now for a circle, no matter what line we use, the circle is going to be symmetric with respect to mirror symmetry as long as that line passes through its center. And so in the examples we looked at, the circle does have symmetry with respect to reflection in the y-axis, the x-axis, the line y equals x, and the line y equals negative x. So we will use the symbol sigma sub infinity to describe the mirror symmetry of a circle. Now for an ellipse has mirror symmetry in the y-axis and in the x-axis, but not with respect to the line y equals x or y equals negative x. For a hyperbola has mirror symmetry with respect to the y-axis and with respect to the x-axis. But not with respect to the line y equals x or y equals negative x. And finally, for the parabola has mirror symmetry with respect to the y-axis, but not with respect to the x-axis or any of the lines, y equals x or y equals negative x. So to summarize, a circle has sigma infinity symmetry. An ellipse, we have sigma x equals 0 and sigma y equals 0. Now, if we're not in a given coordinate system, we may simply say sigma v with respect to a vertical line and sigma h with respect to a horizontal line that passes through its center. And for a hyperbola, we have the same symmetries, sigma x equals 0 and sigma y equals 0, or if we don't care about a particular coordinate system, sigma v and sigma h. And finally, the parabola has reflection about the line y equals, has symmetry with respect to reflection about the line y equals 0, correction, the y-axis, which is x equals 0. That is with respect to a vertical line. Okay, so we have talked about sets in general. There is a particular term that's used often in geometry for a particular set, and so we define that set. A locus is a collection of points. A collection or a set of points that satisfy a particular geometric condition or rule. So the term conic section, as we have discussed, refers to a shape that is generated in three-dimensional Euclidean space by the intersection of a plane with a right circular cone. The term conic refers to a shape generated in the Euclidean plane by satisfying a property concerning distance. So for now, we will accept that there is a possible distinction between a conic and a conic section, but in fact, we'll see later that they are the same. So we'll end here for now. Next time, we will continue our study of conics. So I hope you have enjoyed the first lecture.